Yes, our next talk is also another topic that is traditionally in the journals in the Power Electronics Society not given enough attention to, and that's just the protection from high power to low power and the emerging things that are happening in the field. We know that renewable energy is being put in, and there's putting a lot of stress on the protection of existing infrastructure. And so it's a field that we have to take a look. And Jean-Francois Dupama is, Dr. Dupama earned his PhD at University of Lyon in France. He has a broad background in research from wide bandgap to recently, for a long time, protection of both high power to low power circuits. He has recently moved from Vice President of Research of Mersen USA, which is one of the largest circuit protection manufacturers, to the headquarters, to the global Vice President for Research. So thank you, and welcome.
Thank you, Brad. I think the first introduction I like because the first slide says everything can fail, so this is good for fuses. I'm not going to go into too much detail on equation this morning. I would like to give you a trend of what exists today. It's really an overview without being too much technical, bringing you to the interest and sharing with you the fact that we have solution when things will fail. Fuse is the last resource to avoid a big explosion. So, outline of this presentation is, I just want to remind everybody what we call fuse voltage rating and current rating. I have strange question from customers sometimes. Why do you put a voltage rating on the fuse? And I will explain why. Basic fuse technology, again, without going into too much detail. The trade-off that fuse engineer application have to face every day, the on state and the off state. And then after the trend that we see from our customer and also from renewable energy, PV, storage energy, high voltage drive, everything is going DC. And there's a trend in DC application, and I will explain to you, and I also will share with you the solution that we can bring to our customer. Let's remind everyone that, to give an example, I use the water tank. The potential in an application can be seen as the height of the water. The fuse is what we put on the tube that let go of the water. And the idea is how can we break this water flow? So typically what we create with the fuse is we have to bring the tube above the level of the water, and then only at this time you will stop the water flow. So the idea is to, in this slide is to show you that creating a voltage across the fuse that is above the voltage of the application, that's the only way to stop the current. So I will explain to you in detail a little bit after. Fuse technology, basic fuse technology. All the fuses are built the same way. So we have a tube that could be a GMG body or ceramic body, depending on the standard, the application, the customer, the experience. We have two terminals, copper or brass. We have what we call the fuse element that carry the current. We have two types of technology on semiconductor fuse. A question, also a comment is, we had a booth and people say, you do semiconductor fuse, what type of semiconductor do you use? We say, I don't use semiconductor in the fuse. When we say semiconductor fuse, we mean fuse for the protection of semiconductor. There's no semiconductor in the fuse. It's a silver or a bimetal. Bimetal is a mix between copper and silver. So I disappointed some people, but it's a passive component. It's for the protection of semiconductor. So typically on high voltage or high current rating fuse, we have a bunch or a series of fuse elements in parallel. The higher is the rating of the fuse, the more element you will put it. We have a multitude of elements in parallel because when the fuse melts, you have to dissipate that energy in the field. So the way you dissipate the energy, you have fuse elements that melt. We are surrounded by sand, what we call the filler, and the sand will transform sand to glass At this time, you quench the energy, you clear the fault. It looks easy, but it's almost 100 years of experience and testing. Here an example of what we call the square body technology. It's mainly an IC standard fuses. Used also in US more and more. You can get big, large rating on this type of technology. We have what we call the striker, the micro switch if the customer or if the end user wants to know if the fuse has melted. I have funny questions sometimes. The guy says, if you push back the striker, does he trick the fuse back? I say, no, you have to replace the fuse. It's why I think sometimes it's good to remind what the fuse it is, because we don't learn that at school. By experience, people, they don't know, and when they are facing with an application, we are here to help. So sometimes it's good to remind everybody that the fuse exists and how it works can help. So, when I was a young engineer, I was facing this question every day. Customer call and say, I need a fuse that lasts forever, and I need a fuse that will protect perfectly. And I said, it's impossible. And why it's impossible? The way we design fuses, we have a fuse element, again, silver or bimetal, Froulet and we say copper and silver. And to control the way or the area where the fuse melts, we create what we call reduced section here. The reduced section, the current density is high, so the temperature across the reduced section will be high. So we know where the fuse will melt. And then to increase the voltage of the fuse, each reduced section will create about 200 volt, 150 volt when it's melt. So you know that if you need to open 600 volt, you need 4 minimum. So the idea is to push the fuse at the limit of near the melting point to make sure it's quick to react. Means if you have an overload, it will be quick. But the more you push to the limit of the thermal, the more you will fatigue the fuse. You have what we call the mechanical fatigue. You have what you call the thermal fatigue. So the trade-off is always the same.